for number 5, the main trick to this problem is right here, that the normal boiling point, by definition, delta G is 0. Normal boiling point. Memorize that. Okay, so to do the problem, we're going to take a look at this standard equation, replace delta G with 0. I personally like to rearrange my equations, so that's what I'm going to do. I'm going to add this term to both sides. Now I'm going to divide each side by that term. Now I'm going to substitute the values, but please note I had to multiply the top term by 10 to the third because the values that were given for, I'm sorry, I was thinking, sorry, sometimes it's painful. The values were given for delta H were in terms of kilojoules. All right, that should have an H on it. And the values that were given for delta S, well, that was in terms of joules. So you have to convert one. Doesn't matter to me which one. I chose to convert kilojoules. So if I take kilojoules, I know that for every 1 kilojoule, I really wish I had my pen. I'm not driving to LaGrange in this weather, is 10 to the third joules. So that's why I had to multiply this numerator by 10 to the third to get the units to cancel out correctly. Once I did that, I had 331 Kelvin, which is really close because the normal boiling point of bromine is really 333 Kelvin, but whatever. I can live with these numbers. Since that last one's so short, I thought I'd throw another one up there. Okay, so he has an equation where he uses HAC for acetic acid. But since it's a weak acid, I prefer to use what I have here, which is HA. He's also included water, and technically he's correct, but I prefer to use this one for the ionization of a weak acid. Either one's fine, but I'll be using the starred one. Now there's a definition that goes along with this, because at equilibrium, there's a couple of definitions you need to know. At equilibrium, the value of G is 0. That is the lowest energy state possible. So Gibbs free energy is 0. This term, 0. And because we're at equilibrium, the reaction quotient Q will no longer be used. We'll be using K. So there's our equation. This problem required that you know those two things. Once you know that information, it's basically just a plug and chug problem. Now, I usually think of the R value, 8.3145, as the energy R versus the ideal gas law R, which are the same values if you rearrange the units, but never mind. 8.3145, see there's pi in the middle, times 25 degrees Celsius converted to Kelvin times the natural log of the Ka value. And then plugging that into your calculator, you should get that, but Gibbs free energy is usually given in kilojoules, so I divided by 1,000 to get 27 kilojoules. After giving this question a lot of thought, I think this is the best equation you should use for this. Now, getting gold to vaporize at all is a nightmare, much less at 998 degrees, well, no degrees, 998 Kelvin. Let's give this that with a... So, using this equation, pressure at 1, I'm going to use 1 atmosphere, because then the pressure 2 is the vapor pressure I'm solving for. We know what delta H is. It was given to us in the table. Temperature, well, at standard states, if the pressure is 1 atmosphere, the temperature is 25 degrees Celsius. That's 298 K. And they gave us the second temperature. I know the value of R is 8.3145, so this equation should do the trick because it has everything I need, and I can ignore the entropy values given in the problem, which won't help us at all, as far as I'm aware. So I set the equation up, solved for x, and if you want me to show you later how to solve for x, I'd be happy to do so. But solving for x, I end up with that pressure, which really doesn't seem out of line. I mean, that is a ridiculous pressure. But think about it. Getting a gold bar to vaporize is a really difficult thing to do. That said, that's the best I have on this problem at the moment. If I come up with anything better, I'll let you know.